All right, so last class we learned all of our ionic naming conventions. It was a lot. We just do binary ionic compounds. We've got two options. We've got metals or cations, if they're not metals. We've got metals or cations that only have one charge. That's not the one that we see here on the screen. For those ones, we just write the name of the metal and then the base name of the anion, change the ending to IDE. We are looking at here on this slide if we've got something that can take multiple charges, which is most of our transition metal block and some of the things that are under our non-metals section, the right side of the periodic table that are metals. Some of those things also fall in there, like lead, except for scandium, zinc, and silver. And for these ones, it's still the name of the cation, the metal usually, and if it's a cation metal, we write the Roman numeral in parentheses as well. And then we change the base name of the anion if it's a nonmetal to IDE, or we can also have polyatomic ions. Many of these have to be memorized, so there's a lot of naming to memorize. We talked about oxyanions. With oxyanions, we've got basically four forms. We've got the one that you would memorize with the arrows here, the ATE ending. Those are the ones that I recommend that you memorize. If you've got the green sheet handout, they're all listed there for you. And if we add one oxygen to whatever our ATE ending is, we add the prefix per. The charge doesn't change. The nonmetal doesn't change either. All that's changing is the number of oxygens that we have, and we added one, so we add the per prefix. If we go from the ATE form and we subtract one oxygen, then it turns into the ITE form, the ite form. The charge also doesn't change. If we go one further past the ITE form, so in this case BrO2 minus to BrO minus, then we add the hypo prefix to our bromide. So this would be hypobromite. Again, the charge doesn't change. And this works for all of the oxyanions. Some of these forms probably don't exist, but we wouldn't know that. So they could show up on the exam even if they don't exist. I would just expect you to follow this naming convention pattern. There are also hydrates, things that have water. And our hydrates, we had this dot, some number, and then H2O, H2O being the hydrate part of the hydrates. We call the water the H2O hydrate, and we've got some prefixes that we add on. So we do our normal ionic compound naming convention. We add a prefix for however many hydrates we have. We did some examples of those. Now moving on to our second category of things that we can name are molecular compounds. So our molecular compounds are all going to have a relatively simple form. Part of the issue with molecular compounds, the reason we can't use our ionic naming convention is that the formula can't be readily determined just based on the constituent elements, because we can have multiple combinations of them, as shown here for nitrogen and oxygen. Those are just a couple of unique molecular compound combinations that we can come up with. So for molecular compounds, we are going to be dealing with relatively simple molecular compounds. So if we have binary molecular compounds, where we only have two nonmetals, and there's no charge, then we use numerical prefixes. And these are the same as for hydrates. So our molecular compound naming is, in my opinion, very easy. All that we have to know is what are our numerical prefixes, what are the element names or the symbols. The more metal-like element goes first, generally the element with the smallest group number or the smaller group number, because we've just got two things. And there's you can look up tables of what comes first, and you could memorize the order of things that come first, but I don't think it's worth spending a lot of time on that. You'll just kind of pick it up as you use it, hopefully. So our binary molecular compounds, we've got prefix for however many of our first element we have, space. Prefix, the base name of the second element, change the ending to IDE. And we've got one exception. there's only one atom of the first element, then mono is typically omitted. So NO2 is nitrogen dioxide. We omit the mono prefix. So rather than mononitrogen, since it's the first thing that shows up, we omit the mono. It's just nitrogen. We've got our prefix for 2, which is di, since we've got 2 oxygens. The base for oxygen is ox, and we change the ending to IDE. For H2O and NH3, we're typically just going to use their common names, water and ammonia. There are other names that you can find for them depending on which naming convention you choose to use. All right, let's name these compounds. This compound, N2O5. How many of our first element do we have? 2. What's our prefix for 2? Di. And then we've got the name for the element, nitrogen. N is nitrogen. And we've got how many of our second element? 5. What's our prefix for 5? Penta. And then we have the base name for oxygen, which is ox. And then part of our rule, we change the ending to IDE. So dinitrogen pentoxide would be the name. There's another thing that I don't think was mentioned in the slides. If you've got a prefix that ends, for example, in A or a vowel going into a base name that's got a vowel, we would usually just drop the A in the penta, so it'd just be pentoxide. If you write pentaoxide, people will still understand what you mean, so it's not a big deal. I wouldn't take points for that. All right, we want the formula for phosphorus tribromide. What is our first element? Phosphorus. How many phosphoruses do we have? We've got 1, so P for phosphorus. And then our prefix 3, tri, tells us that we've got 3 of what element? Bromine. So this is PBr3. Molecular compounds. Arguably easier than ionic compounds. Arguably. So that's all of molecular compounds for binary molecular compounds. There are some other ones that we'll learn about that are also molecular. But those are like the simplest molecular compounds. Now acids. Acids is our third category. Acids are also molecular compounds. These are not the other type of molecular compounds that I was talking about. There's a secret third thing. So acids are molecular compounds that release hydrogen ions, H+, when they are dissolved in water. Acids are composed of hydrogen. They have to release a hydrogen. Usually written first in their formula, and then one or more nonmetals written after that. So acids often start with H. That's generally, for this level of chemistry, our big indicator that we're dealing with an acid. It starts with an H. So for example, HCl is a molecular compound. It's got hydrogen, which is a nonmetal or considered a nonmetal, and chlorine, also considered a nonmetal. When that's dissolved in water, it forms H+ ions. It forms Cl- or chloride ions. Aqueous, the AQ part, means dissolved in water, like aqua. Okay, so acids have some characteristics. Acids have a sour taste, and they dissolve many metals. However, hashtag not all metals. So things like gold, silver, platinum, palladium, rhodium, iridium, and other precious metals typically don't dissolve in acid, which is great, because then if you spill acid on your expensive jewelry, it hopefully doesn't dissolve. Again, our formulas for acids generally start with H. This is not all-inclusive. There are many such acids that don't start with an H. But for now, that can be our indicator that we're working with an acid. When we're naming acids, again, this is typically something that starts with H. There's two naming conventions. So we've got binary acids, we've got oxyacids. Binary acids have how many elements? 2. The name binary, meaning two elements. One of them being hydrogen, the other one being a different nonmetal. We've also got oxyacids. Oxyacids contain an oxyanion. Like sulfate, which is SO4 2-. So any of those where it's a nonmetal plus some oxygens and it's got an overall charge, that's our oxyanions. So we can have acids that are made with those, and those are our oxyacids. Both of these will have hydrogen showing up as their first element most of the time. The easier of the two, in my opinion, the binary acids. For the binary acids, we use the prefix hydro. Hydro is the unique identifier for a binary acid. So this is our key, our clue. So we're going to start our name off with hydro. We use the base name of our nonmetal, and then we change the ending to ic and add acid. The word acid at the end, this is a dead giveaway that we're working with an acid. Big clue here. I just think that's funny to say. So, pointing out the obvious, we do change the ending to ic, ic. All right, let's name the acid HF. HF is what kind of acid? What? Binary. Binary acid. What do we use for our binary acids? Yeah, we use the hydro prefix. And then we're going to need the base name for fluorine, F. So hydrofluor, not hydroflower, hydrofluor, the U comes first. Hydrofluor, change the ending to ic and add on acid. Hydrofluoric acid made popular in the hit TV show Breaking Bad. It's great for dissolving bathtubs. All right, and then we want to write the formula for hydrosulfuric acid. What kind of acid is hydrosulfuric acid? It's a binary acid. How do we know it's a binary acid? Because of the hydro prefix. That's how we know it's a binary acid. We also know it's a binary acid because it says at the top of the slide, naming binary acids. And then we've got what element? Sulfur. So we've got sulfur. This is hydrosulfuric acid. Since it's got that hydro prefix, that means that we've got an H in front. And then we don't have F, we have S. What charge does hydrogen make when it's an ion? +1. What charge does sulfur have when it's an ion? It's a 2-. So if we put one H plus and one S2- together, are we going to have a neutral compound? We are not. How do we fix it? We swap and drop or we crisscross. And this puts a subscript of 2 behind our hydrogen. So this is H2S. So it must be neutral. We could also have compounds like H3P, this is still a binary acid because we only have 2 elements. So don't get confused that we have like more than 2 hydrogens or something and think, oh, it's some secret third thing. It's not a secret third thing. It's still just a binary acid. Still binary because only 2 elements. Any questions about molecular compounds or binary acids? All right. Now to have fun with oxyacids. Okay, so oxyacids, if you know your oxyanions, are not that bad. Until you've got your oxyanions memorized, the green sheet will be your best friend. So our rules for oxyanion acids, oxyacids, is that if the ending of the ion ends in -ate, it turns into -ic. So 8 turns into -ic. And if the ending is -ite, then we change the ending to -us, O-U-S. So 8-ic, -ite-us. And the dead giveaway that it's an acid, we write acid at the end. A note, we don't change prefixes. So if we have per sulfate, we don't change anything about the per part. It's just per sulf, and then we change the -ate to -ic. Pure sulfuric acid, per sulfuric acid, for example. I think we'll see an example, hopefully, in here. And just because I didn't mention it or write it out explicitly, the number of H's needs to balance the charge. So the oxyanion charge will get balanced out by an appropriate number of hydrogen ions. All right, our oxyacid namings. We've got the acid HNO2. How do we know it's an acid? It starts with H. H in front means it's an acid. So we've got HNO2. We have an oxyacid, so we need to know the name of our oxyanion. NO2 with a 1- charge looks like NO3 with a 1- charge. NO3- is the one that we would have memorized, which is nitrate. How did we change from our ATE form, nitrate, to the one that we have? What did we change? We took away 1 oxygen. So taking away 1 oxygen, we changed the ending from -ate to -ite. So this is nitrite. And our rule is that -ite turns into -us, and we add acid at the end. So this is nitrous, nitrous acid. And we want to write the formula for perchloric acid. What kind of compound is perchloric acid? It's an acid. What kind of acid? An oxyacid. It's an oxyacid, 1 sign. We've got a per prefix. We're only going to see the per prefix in oxyacids. We also don't have hydro. No hydro means it's not binary. So our other category that we know so far is oxyacids. So it must be an oxyacid. we would look for something that has perchlor in it. So perchlor, if the ending is ic, what does ic come from? Ic comes from 8. So this would be perchlorate. We'd have to figure out what perchlorate is. It's got the chlorate part in it. That's our 8 ending. The per in front means we add 1. So let's figure out what chlorate is. We look at our green sheet. Chlorate is ClO3 minus. And the per means add 1 oxygen. So this is ClO4 minus. That's the perchlorate part. And then the acid part, we put a hydrogen on the front. It's a 1 minus charge, so we just add 1 H plus. So this is HClO4, perchloric acid. You don't have to write out all of these steps. I'm just trying to explain a lot of the steps or clues or keys that you might use. Questions about oxyacids? The oxyanion naming is arguably the hardest part of oxyacids. Okay, so if we're writing formulas, when the name ends in acid, the formula starts with an H. We'll have H or multiple H's in front. We would write the formula as if it's ionic, so including the charges. Swap and drop as necessary, or crisscross as necessary to get them to balance out, to get a neutral charge. For an oxyacid, if the ending is ic, the polyatomic ion ends in 8. If the ending is us, then it must have had ite. So it's just 8 to ic, ite to us, but in the other direction. How can we tell the difference between HCl, or what would we call HCl, and what would we call HClO3? HCl is a binary acid. So it's hydro, the base name of the nonmetal, change the ending to ic, add acid. What's HClO3? ClO3 minus is chlorate. The 8 ending gets turned into ic, and we add acid at the end. What if we didn't have the hydro prefix in front of our hydrochloric acid? Now they're the same thing. Right, so this is why we have this hydro prefix, is so that we can tell the difference between HCl and HClO3 and other things that follow the same pattern, our 8s and our whatever our binary acids are. So the hydro lets us distinguish these from each other. So part of the reason that we need the hydro prefix. All right, some extra examples. We can also have things that follow the binary acid convention. Sort of loosely. It can include some polyatomic ions. Note this is the binary naming convention, the nomenclature. So hydrocyanic acid, the hydro at the front lets us know that it's a binary acid. And then we've got the color blue, bluish, cyanic. We would need to find something that's cyanic-ish. And if we look at our green sheet at the bottom in our polyatomic ions, we would find cyanide, which is Cn minus. So this cyanic came from cyanide. So we've got a binary acid with Cn minus in it. So H plus, Cn minus, those can combine in a 1-to-1, HCN. We've also got phosphoric acid. What kind of acid is phosphoric acid? It's an oxyacid. It's an oxyacid because we don't have the hydro prefix. So we need something that has the phosp in it. The ending is ic. Where did ic come from? So ic from 8. So we're looking for phosphate. So phosphate, we would look at our green sheet. Phosphate is PO4 3 minus. And we would be pairing this with H plus. So we need 3 hydrogens in front, H3PO4. And then last but not least, we've got hypochlorous acid. The hypo in the front letting us know that this is definitely an oxyacid. So we need the oxyanion of chlorine, ClO3 minus is chlorate. The OUS ending would have come from ITE. And the hypo in the front, meaning one less. So we have to go down to our ITE form and then down to our hypo and ITE form. So we're going to lose 2. So ClO minus is hypo. Chlorite, so ClO with the 1 minus charge, H plus has a 1 positive charge, so HClO. Questions about acids and how they're named? Okay, here's a grand overview of all of the inorganic nomenclature. This is the order that we covered them. We covered ionic first. We've got things that form one type of ion, things that form more than one type of ion, and we've got different rules and naming conventions, and we've got some examples of those. Today we talked about the molecular, things that are nonmetals only. That's where we use those prefixes. We omit the mono if it's the first prefix, and we change the ending to IDE. For our acids, we've got 2-element or binary acids. We get the hydro prefix for those. The ending changes to ic. For our oxyacids, these contain oxygen or an oxyanion. If it's got an 8 ending, ATE ending, that turns into an IC or an ic ending. If it's got the ITE ending, it turns into the OUS ending. So this nomenclature flowchart, which is from your book, could be really helpful for working through these problems, or if you just wanted to memorize a flowchart or like try to put some sort of visual, how do I navigate the names into your head, that could be helpful. When we are working with chemicals, it'll often help us to be able to calculate a formula mass. So the formula mass is the average mass of an individual molecule or formula unit. What kind of compounds have their smallest unit as molecules? It's a very similar name. Molecular compounds. So molecules are the single unit of molecular compounds. Formula units are the singular unit of ionic compounds. We could also call this formula mass, the mass of one formula of the chemical. We could also call it the molecular mass or the molecular weight, the weight of a molecule or the mass of a molecule. Just whatever our smallest unit is. To calculate the formula mass, we just add up the masses of all the individual parts. So we'll have this series of things that we add up. However many of atoms of one of the elements in the formula times its atomic mass. So this number that's below our symbol on our periodic table. And then we're going to add to that the number of atoms of our second thing times its mass. And we can add as many things as we want to, up to 118 terms if we wanted to get into theoretical things. So for example, calculating the formula mass of calcium nitrate. To calculate the mass of calcium nitrate, we first need to figure out what is calcium nitrate, what's the formula. So we're going to figure that out. Any ideas what kind of compound we're working with calcium nitrate? What kind of element is calcium? Calcium's a metal. So this is ionic, because we've got a metal in there. So calcium is Ca, and what charge is it going to form? It's going to form a 2+. We know it always forms the same thing because we didn't specify after the name what the charge is. So it's always calcium 2+. It's in our column 2, our group 2, our alkaline earth family or group. And then nitrate is what? It's an oxyanion because it ends in ATE. We can find it on our green sheet in our oxyanions section at the top. It's NO3-. And then we can crisscross these to get Ca with an invisible 1. And then we've got multiple of our nitrates, so we have to put that in parentheses. So our nitrate, and we've got how many nitrates? 2 nitrates. So this is just getting to our formula so that we can find the formula mass. Now we have to count up how many of each thing do we have. Well, we've got calcium with an invisible subscript of 1. Calcium, we've got 1 of them. We've got also in here nitrogen. How many nitrogens do we have? We've got 2 nitrogens. We've got just 1 in our nitrate, but we've got 2 nitrates, so 2 times 1. For nitrate, we've got 2 of them. And then for oxygen, we've got 3 oxygens per nitrate. We've got 2 nitrates. So 2 times 3, not nitrate again, oxygen. We've got 2 times 3 for 6. So we've got 1, 2, and 6 respectively for our calcium, nitrogen, oxygen. And then we have to find on our periodic table, whichever one you care to use. I'm going to use the yellow sheet one. We have to find their atomic masses. So we find calcium over in column 2. It's got an atomic mass of 40.08. Does anyone know what the unit is? AMU. We've got 2 nitrogens. Nitrogen is over on the right side. It's in group 15 or 5A. It's 14.007 with units of AMUs. Oxygen is right next to it with an atomic mass of 15.999 AMUs. So we're going to add up the 3 terms that we've got here. 1 times the 40 and change, 2 times 14 and change, 6 times almost 16. And that together will be our atomic mass, or our formula mass, sorry. We could also write it out side by side like we saw it in the previous slide. And I'll let you in on a little secret. You don't have to use any of those parentheses. Your calculator will do it correctly without them. Any questions about setting that up? You will need to know how to calculate a formula mass, because we're going to be using that, I would say, a pretty decent amount. So our calculator should tell us that this is 164.088 AMU. Is that our final answer? What about significant figures? We can do significant figures for molar masses. Generally, I just say don't worry about it, because it's really annoying, and you shouldn't ever be using numbers from a periodic table that have few enough decimal places that it limits your number of significant figures. But if we really wanted to, we could round this for significant figures. It would be there because of the 40.08. Any questions about formula mass? All right. We also will be interested in the molar mass of a compound. The molar mass of a compound, the mass in grams of 1 mole of its molecules or formula units, is numerically equivalent to its formula mass. The only difference is that formula mass has units of AMU, molar mass has units of grams per mole. That's, I think, really the only significant difference. If you can find a formula mass, you can find a molar mass. You just make the units grams per mole instead of AMUs. I think we talked about previously why these are the same. So if we want the molar mass of ammonia, ammonia is the common name for NH3. For nitrogen, we've got 1 of them. For hydrogen, we've got 3 of them. Since we're doing a molar mass instead of a formula mass, we're going to be using grams per mole instead of AMU. And this is 17 and some change. I forget what it is exactly. 17.031 grams per mole. Initially, if you haven't done this a lot before, it'll be kind of slow. It might be a little clunky. As you start to get used to it, eventually, hopefully, you'll get to the point where you don't have to write anything down. You just plug the numbers in your calculator. It tells you the answer. Okay, so something we can do with molar mass is we can count molecules by weighing or massing them. So in combination with Avogadro's number, we can use this to determine the number of molecules in a given mass, just like we determined the number of atoms in a given mass. So for example, we want to find the number of ibuprofen molecules in a tablet containing 200 milligrams of ibuprofen. Aspirin, for those of you that like the candy version. I say it's a candy version because it's sugar-coated. So I think aspirin tastes pretty good. Anyway, that's a little about me. So carbon, we've got 13 of them. Hydrogen, we've got 18 of them. Oxygen, we've got 2 of them. So we pull out the masses for each of these. Carbon, 12.011 grams per mole. Hydrogen, 1.008 grams per mole. Oxygen, 15.999 grams per mole. As you might be able to tell, once you work with them enough on the periodic table, you also memorize the atomic masses, which speeds up the calculations significantly because you don't have to reference your yellow sheet. I don't expect you to be super fast at these yet. But once you start working with them more, or if you decide to spend some time memorizing them, that'll speed things up too. Okay, and then we sum that. And we get 206.285 grams per mole. This is a conversion factor that we're going to need, our molar mass. What are we starting with in this problem? What's our starting thing, our given? 200 milligrams. And what are we trying to find? The number of ibuprofen molecules. So we're going from milligrams to the Greek hero molecules. So from milligrams, what could we convert milligrams into? Grams. 1,000 milligrams equals 1 gram. From grams, what can we go to? Moles, using what? Not Avogadro's number. The molar mass that we just calculated. And from moles, we can go to molecules using what? Avogadro's number. N sub A. So starting with 200.0 milligrams, there's 1,000 milligrams in 1 gram. The milligrams part goes on the bottom, so the units cancel. Now we've got grams. We need to get to moles. Are we going to multiply or divide by our molar mass? The grams part is on the top in our molar mass. We have grams on the top, so we need to divide. we put the number part and the grams on the bottom. So that our grams cancel. Avogadro's number, 6.022 times 10 to the 23 units per mole. The per mole means that the moles would go on the bottom. We're going to multiply. There's also like a logical way that you could figure out that we're multiplying by Avogadro's number. You can't have less than one molecule of something, so it would have to multiply so that we have a big number instead of an extremely tiny number. The unit here is going to be molecules. And our moles cancel. So 200 divided by 1,000, also divided by 206.285 times Avogadro's number. We get big number. Times 10 to the 20 molecules. Questions? All right, we've got more stuff here that I think is not going to show up on the nomenclature worksheet that we're starting today. So I'm going to skip past a bunch of the maths calculation stuff to organic compounds, and we'll come back and hit this on Thursday. Okay, so skipping ahead. Early chemists, not people who got up, before the sun, but just chemists who are now dead, divided compounds into two types, organic and inorganic. The historical origin of this is that compounds from living things were called organic, compounds from non-living environment were called inorganic. So things from like rocks, for example, which aren't alive but are cool. They found that organic compounds were more easily decomposed than inorganic compounds, and they were pretty easily able to synthesize inorganic compounds in the lab, but not organic compounds. Today, organic compounds are all over the place. They're pretty easy to synthesize and buy. Organic compounds, typically, organic means that we're working with carbon. Carbon's like the backbone, the base for organic compounds. So we're going to have carbon and hydrogen, and we'll sometimes have some other things like oxygen, nitrogen, phosphorus, and sulfur. But the key is carbon. Since we are carbon-based life forms, not silicon-based life forms, like show up in an episode of Star Trek. So carbon is the backbone, the basis. Carbon bonds in organic compounds are almost exclusively covalent. When carbon bonds, it forms 4 covalent bonds. Carbon likes having 4 bonds. You can distribute that into any number of single, double, or triple bonds as long as the total number of bonds adds up to 4. And it'll typically form chains, branched, and ring structures. So chains would just be carbon bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon, for example, but in a straight line. Branched would be also carbon bonded to carbon, but that one of those might be bonded to another carbon. There's extra carbons now all of a sudden. So those would be examples of branched. And then ring structures are carbon bonded to carbon, but like in a circle or a ring. And you can have different numbers of carbons in the ring. 6 is pretty common, 5 is also pretty common. 7 and 8 are also feasible. 3 explodes, so don't do 3. So here's some structural formulas of some carbon compounds, some organic compounds. So one of them, propane. We've got 3 carbons bonded together in a chain. Isobutane, we've got 4 carbons. Our naming is going to be based on our carbons. We are going to learn some naming conventions for some of these compounds. That's why I skipped to it. Cyclohexane, the cyclo prefix meaning that we've got a ring structure. So we've got 6 carbons all in a ring here. And we've got also some double bond options, a triple bond option, and something that's not carbon or hydrogen in there as well. Lots and lots of options with these carbon-based structures. Part of the reason that organic chemistry is famously very difficult, you've got a lot more complex naming conventions in there. Okay, so naming conventions, nomenclature for hydrocarbons, things that have hydrogen and carbon. Hydrocarbons are just hydrogen and carbon. So we can have hydrocarbons and we can have functionalized hydrocarbons. So somebody put the fun in functionalized hydrocarbons, and that fun is something other than hydrogen and carbon. So including things like oxygen, sulfur, nitrogen, phosphorus. Those somethings are also called heteroatoms. Hetero like other or different. So heteroatoms, just different atoms, things that aren't carbon and hydrogen. Hydrocarbons are organic compounds. They contain only carbon and hydrogen, as we mentioned. They are common fuels. So they show up in oils, they show up in gasoline, liquid propane, natural gas, which is methane, other gases that are flammable and can be used as fuels. To name hydrocarbons, we've got a couple of categories. First up, we've got our single bonds only. So if we've got only single bonds, then we've got a group of hydrocarbons called alkanes. The ending part is the most important part, the anes part. So anes is single bonds. We've also got alkenes. We've got double bonds. We've got alkenes. The enes part at the end meaning that they're double bonds. And we've also got triple bonds, which are the ines. So alkynes. They've got all kinds of bonds. Triple bonds in particular. Our general and our most basic form for hydrocarbons is that we've got a base name that's determined by the number of carbon atoms. There's a naming convention for these. It's different than things that we've seen before, so you kind of just have to memorize these for the most part. Once you get past like 10, then it starts to get really systematic. But before 10, it's like all different stuff. And then the suffix, the ane, the ene, the ine, depending on if there's multiple bonds. Questions so far? Cool, we're having fun. All right, more fun. So the base name depends on the number of carbons that you get to memorize. Yay, more memorization. Okay, so we've got meth, which means 1. We've got eth, which means 2. We've got prop, which means 3. We've got bute, which means 4. Pent makes sense, hex makes sense, hept makes sense, oct makes sense, non makes sense, dec makes sense. These are from pent to dec. Those are all the same as our like hydrate prefixes. It's the same sort of form. So meth, eth, prop, but. These are new ones. The other ones follow the same form. So pent, hex, hept, oct, non, dec. Same order as our hydrate prefixes, our molecular compound prefixes. And the same numbers too, which is important. So this is for the base part of the name, up to 10. And then for alkanes, single bonds, it ends in ane. So alkanes have single bonds only. Alkenes has a double bond, one or more. Alkyne has triple bond, one or more. Okay, so some common hydrocarbons using these names. Computer, enhance. So we've got CH4. We've got one carbon. One carbon means that we use our meth base name. One carbon can only have single bonds when it's just a hydrocarbon. So it's got 4 hydrogens on it. It's a hydrocarbon. So meth, the ending is ane because it's single bonds. So methane. If you have a gas stove at home, chances are it runs on methane, unless you live outside the city and you're not on a gas service line. We've got propane and propane accessories. So propane, the prop base name is for 3. Propane is typically what's used for grilling outside. You buy in the big cylinders at a gas station, or you trade them at a gas station. The ane ending also meaning single bonds. So if we look at the structural formula, we've got our 3 carbons in a line. They're all lined up. You can't branch these even if you wanted to. And we've only got single bonds between them. So this is propane. Then we've got N-butane. This N prefix means normal. And that means that it's straight chain, aka not branched or cyclical. So if you see the little N, usually it's italicized in the front. So N-butane, the but prefix, meaning that we've got 4 carbons and they're in a straight chain. That's why we put the N for normal on the front. It just means that it's a straight chain of the carbons. Going down to ethene, the eth prefix means that we've got 2 carbons. The ene ending meaning that we've got a double bond. So we've got a double bond between our carbons. The carbons are the only thing in there that can have double bonds. And then to make up the rest of the bonds, I didn't point this out for the rest of them, to make up the remainder of the 4 bonds that our carbons want, we just add in the necessary number of hydrogens. So we add hydrogens to carbons until they all have 4 bonds, 4 total bonds. And then we've got ethyne, so 2 carbons of the eth prefix, the YNE ending, the ine ending, meaning that we've got a triple bond between our carbons. So our carbon on the left here has a triple bond, that's 3 bonds. And it also has a single bond for 4 bonds. It's got its 4 bonds that it likes, so it's content. The other carbon has the same treatment. Questions about any of those? It's a lot. That's part of why we've got the nomenclature lab. I think these show up in there, and that's why I wanted to talk about them. We've also got functionalized hydrocarbons. So functional groups. Functional groups all have specific names. There are so many functional groups. We're not going to use most of them. I think we kind of are just going to mention them, and I'm not going to make you memorize them. But if you're going to take organic chemistry, you'll get to learn lots of functional groups. Even the carbon-carbon double or triple bonds are sometimes considered functional groups, but you'll still get to know those. A group of compounds with the same functional group forms what we would call a family. So the OH just as an example, OH is alcohol. So if you see an OH at the end of a formula, that means that it's an alcohol. So CH3OH is methanol, for example. The all ending because it's got an alcohol. Meth because we've got one carbon. The an or ane part because we've got all single bonds. And then the all ending because it's an alcohol. Methanol or wood grain alcohol. This is the one that you cannot drink. If you drink it, go to the emergency room and also take some shots and don't drive yourself. C2H7OH, I'm not used to writing them. This has two carbons. They're all single bonds. And we've got the all ending because it's an alcohol, ethanol. Ethanol is the one that you would typically be drinking if you drink. That's the most common alcohol for drinking. So those would be a family of alcohols, as an example. Look at that. They didn't do the fun one, though. I mean the one you can drink, though. So methanol, isopropanol, prop, because we've got three carbons. The iso means that we're attached to the middle one. There's also lots of fun prefixes in organic chemistry, so iso means that we're attached, in this case, to the middle carbon. We're not attached to one of the end carbons. There's also all of these organic compounds. These are some families, just kind of mentioning that they exist. So ethers that have ether in the name, aldehydes that end in al, ketones that end in -one, carboxylic acids that end in acid, esters end in -ate, amines have amine in them. This could just be kind of nice, like if you just wanted to look at the back of, honestly, any like label for like even skincare products, shampoos, things like that. You'll see some of these show up in there. All right, so before we wrap up for the lecture for today, let's draw the structural formula for nonane. What does the non mean? Non for 9, and ane means what? It's an alkane. Alkanes have only single bonds. One of the fun things about just saying nonane is we didn't specify N-nonane, so this could be any branched variety of nonane. Another shorthand that we would typically use, because it's really annoying to have to draw out all those hydrogens, if we just draw lines at the intersection or ends of each line, these are all just carbon. So this is a shorthand that's typically used in organic chemistry so that we don't have to draw out all of our hydrogens or even our carbons. So right now we've got 1, 2, 3, 4, 5, 6, 7, 8, and now we've got 9. So we've got all of our 9 carbons, and then what do we do for the hydrogens? Nothing. We don't write in the carbon or the hydrogens. It's just assumed that the rest is hydrogens. So this is what we could do in the future, just as a preview. What we should do, though, is what I'm going to do now, which is write out all of the carbons. So that's all of our carbons. And I'll do the hydrogens in a different color. So this is setting up the backbone for our nonane. And then we have to fill out, for all of these carbons, the correct number of hydrogens. What's our goal for placing our hydrogens on our carbons? How do we know when we've hit enough? When we've hit 4 bonds for each carbon. So looking at our carbon on the end, it's currently 1 bond. We need 3 more bonds to get up to 4. So we're going to add in 1, 2, 3 hydrogens. And now that carbon's happy. For the next carbon in the chain, it's got 2 bonds already, just with the carbons. So we need 2 hydrogens. And this is a repeating pattern for all of these internal carbons, the ones that are not at the ends. Okay, we're done with all of our internal carbons. And we've got our other terminal carbon, our ending carbon, which has 1 bond with another carbon. And so this carbon gets 3 hydrogens. So that is the full structural formula for nonane, specifically N-nonane. You could also draw it with branched versions. All right, and then for this last one, to which family does this compound belong? We would have to refer to our table, because we didn't learn these ones yet. So referring to our table, we've got a bunch of examples, we've got a bunch of general formulas. We're looking for something that has a functional group on it. We've got this carbon bit here at the end. It's just carbon and hydrogen. That's not the interesting part. It's this part over here on the right side that's interesting. So we're going to find something that looks like carbon with a double bond to an oxygen and a single bond to an oxygen and then a hydrogen, which is an alcohol. And we find that here in our carboxylic acids category. So you've got the carbon double bonded to the oxygen in the OH. This is different from esters. The R prime part here for this ester, R means any alkyl group. So more carbons and hydrogens on the other side, whatever you want to be there. Since we have hydrogen here specifically, this would be a carboxylic acid. And that's as much as we would need to do for this. Questions about any of the fun that we've just had with naming? Great. Then we will stop there and we will return to the maths stuff that we skipped over on Thursday.